Welcome our competent engineer. Welcome our competent engineer to our first part of X training program according to IEC 60079. X training courses have been run in Aberdeen College since 1990 and have developed to the level of sophistication we have today. In its present form, the CompX course has been in operation since August 1994 and has been designed and constructed specifically for the national training of personnel who work with electrical installations and plant in hazardous and/or potentially explosive environments. The objective of the training is to introduce the candidate to operating procedures and techniques and to give candidates and their employers confidence that the candidates are competent to work on electrical apparatus in hazardous or potentially explosive environments. The competence laid down nationally by industry and through this will help make your industry a safer one. First part will cover nature of flammable materials, gas grouping, basic principles of area classification, temperature codes, ingress protection, standards, certification, and marking, explosive atmospheres. First, as a definition of fire triangle. Fire triangle represents the four elements which must be present before combustion can take place. Each points of the triangle represent one of the essential elements which are fuel, this can be in form of a gas, vapor, mist, or dust. Oxygen, plentiful supply since there is approximately 21% by volume in air. Source of ignition, this can be an arc, spark, naked flame or hot surface. Chemical reaction, interaction of two or more chemical that produce one or more new chemical compounds, or alters the properties of the mixed chemicals. Most reaction require heat, pressure, radiation, other conditions, and/or the presence of accelerator. Now we are going to go through the nature of flammable materials. Let us first know how the combustion happens. Combustion will take place if all three elements, in one form or another, are present, the gas and air mixture is within certain limits and the source of ignition has sufficient energy. The removal of one element is sufficient to prevent combustion, as is the isolation or separation of the source of ignition from the gas and air mixture. These are two techniques used in explosion-protected equipment. Other protection techniques allow the three elements to coexist and either ensures that the energy of the source of ignition is maintained below specific values, or allows an explosion to take place and contains it within a robust enclosure. These techniques are addressed in the various sections of this manual. There are many sources of ignition, are varied and include electrical arc/sparks, frictional sparks, hot surfaces, welding activities, cigarettes, static discharges, batteries, exhaust of combustion engines, thermite action, sodium exposed to water, chemical reaction, lightning strike. Combustion will only occur if the flammable mixture comprising fuel, in the form of a gas or vapor, and air are within certain limits. These limits are the lower explosive limit, LEL, and the upper explosive limit, UL, and between these limits is known as the flammable range. An everyday example of this is the carburetor of a petrol engine, which must be tuned to a particular point between these limits in order that the engine may function efficiently. Lower explosive limit, when the percentage of gas, by volume, is below this limit the mixture is too weak to burn, i.e. insufficient fuel and/or too much air. Upper explosive limit, when the percentage of gas, by volume, is above this limit the mixture is too rich to burn, i.e. insufficient air and/or too much fuel. Too lean and/or too rich, the mixture will not ignite. Different gases or vapors have different flammable limits, and the greater the difference between the LEL and the UL, known as the flammable range, the more dangerous the material. An explosive, flammable, atmosphere, therefore, only exists between these limits. Operational safety with flammable mixtures above the UL is possible, but is not a practical proposition. It is more practical to opt. An important definition in our course is the flash point, which is the lowest temperature at which sufficient vapor is given off a liquid to form a flammable mixture with air that can be ignited by an arc, spark or naked flame. Typical values are given below. Second important definition is auto-ignition temperature. Ignition temperature is defined as the minimum temperature at which a flammable material will spontaneously ignite. Ignition temperature, formerly known as auto-ignition temperature, is an important parameter since many industrial processes generate heat. Careful selection of electrical equipment will ensure that the surface temperature produced by the equipment, indicated by the tier rating, will not exceed the ignition temperature of the flammable atmosphere which may be present around the equipment. Typical values of ignition temperature are: does the material density have role? Of course, if a flammable material is released, it is important to know whether the material will rise or fall in the atmosphere. The different flammable materials are compared with air and allocated a number to denote their relative density with air. Since air is the reference, its relative density is 1, so that for a material twice as heavy as air, its relative density will be 2. Therefore, materials with a relative density less than unity will rise in the atmosphere, and those greater than unity will fall in the atmosphere. Materials which rise in the atmosphere can collect in roof spaces, and those which fall, such as butane or propane, can drift along at ground level and possibly into a non-hazardous location, or may collect in locations lower than ground level without ever dispersing. Such locations should be well ventilated in order to avoid ignition due to a stray spark or a discarded cigarette. Knowledge of where a flammable material will collect ensures that gas detectors when fitted will be located at the correct level and ventilation is directed accordingly. Hazardous area classification. A hazardous area is defined as an area in which an explosive gas atmosphere is present, or may be expected to be present, in quantities such as to require special precautions for the construction, installation, and use of apparatus. A non-hazardous area is defined as an area in which an explosive gas atmosphere is not expected to be present in quantities such as to require special precautions for the construction, installation, and use of apparatus. What are zones means? Zoning is a means of representing the frequency of the occurrence and duration of an explosive gas atmosphere based on the identification and consideration of each and every source of release in the given areas of an installation. Zoning will have a bearing on, and simplify the selection of, the type of explosion-protected equipment which may be used. Hazardous areas are, therefore, divided into 3 zones which represent this risk in terms of the probability, frequency, and duration of a release. The 3 zones, as defined in BSN 60079-10, Electrical Apparatus for Explosive Gas Atmospheres, Part 10. Classification of hazardous areas, are as follows. Zone 0, in this zone, an explosive gas atmosphere is continuously present, or present for long periods. Zone 1, in this zone, an explosive gas atmosphere is likely to occur in normal operation. Zone 2, in this zone, an explosive gas atmosphere is not likely to occur in normal operation and, if it does occur, is likely to do so only infrequently and will exist for a short period only. Although not specified in IEC 60079-10, but quoted in APIRP 505, the duration of a gas release, or a number of gas releases, on an annual basis, 1 year comprises circa 8,760 hours, for the different zones is as follows. Zone 2 to 0, 10 hours. Zone 1 to 10, 1,000 hours. Zone 0, over 1,000 hours. In the IEC system, the group allocation for surface and underground, mining, industries are separate. Group I is reserved for the mining industry, and Group 2 which is subdivided into IIC, IIB, and IIA for surface industries. The representative gases for the subgroups are shown in the table below. 2 methods have been used to group these flammable materials according to the degree of risk they represent when ignited. One method involved determining the minimum ignition energy which would ignite the representative gases. The values obtained are relevant to intrinsically safe apparatus. In the table below it can be seen that for group 2, hydrogen and acetylene are the most easily ignited and propane the least easily ignited. The other method involved tests using, for example, a special flame-proof enclosure in the form of an 8-liter sphere which was situated inside a gas-tight enclosure. Both halves of the sphere had 25 mm flanges and a mechanism enabled the gap dimension between the flanges to be varied. During tests, the area inside and outside the sphere were occupied with the gas in its most explosive concentration in air and, by means of a spark plug, the gas inside the sphere was ignited. The maximum dimension between the flanges, which prevented ignition of the gas/air mixture, is known as the maximum experimental safe gap, MESG, and the values for the representative gases are shown in the table below. The more dangerous a gas, the tighter the gap at the flanges has to be. It is important to note that the MESG values are not used for the design of flame-proof apparatus, only the maximum working gaps. The table also shows that these flammable materials fall into the same order for both tests, i.e. in a relative context, hydrogen and acetylene present the most risk and propane the least risk in terms of minimum ignition energy and MESG. Temperature classification. Approved electrical equipment must be selected with due regard to the ignition temperature of the flammable gas or vapor which may be present in the hazardous location. Apparatus will usually be marked with one of the temperature codes shown in the table below. In the table, it will be observed that for each material, the tier rating temperature is below the ignition temperature of the flammable material. Moreover, the tier rating temperatures are based on a maximum ambient rating of 40 degrees Celsius as far as the UK is concerned. For example, apparatus classified T5, based on a 40 degrees Celsius ambient rating, will have a maximum permitted temperature rise of 60 degrees Celsius. In order to avoid infringement of the apparatus certification, the ambient rating must be compatible with environmental ambient temperatures, and the temperature rise not exceeded. A further consideration is apparatus for use in hotter climates, typically found in Middle and Far Eastern countries, which will usually require ambient ratings greater than 40 degrees Celsius. Apparatus for use in colder, Arctic, climates will require a much lower limit to the ambient temperature range, which may be as low as -50 degrees Celsius. The lower the T number, the higher the temperature. Hottest is worst. Coolest is best. For example, if the selected highest T class is T3. Equipment marked with higher T classes is not permitted for installation across this project. Any equipment identified with a T class of T1 or T2 must be reported immediately to your supervisor, inspector, or engineer. Degrees of protection provided by equipment. IP code. Ingress protection. Enclosures of electrical equipment are classified according to their ability to resist the ingress of solid objects and water by means of a system of numbers known as the International Protection, IP, code. This code, which is not always marked on apparatus, consists of the letters IP followed by two numbers, e.g. IP56. The first number, in the range 0 to 6, indicates the degree of protection against solid objects, and the higher the number the smaller the solid object that is prevented from entering the enclosure. 0, 0, indicates no protection and 6 indicate the apparatus is dust tight. The second number, ranging from 0 to 8, identifies the level of protection against water entering the enclosure, i.e. 0 indicates that no protection is afforded, and 8 that the apparatus can withstand continuous immersion in water at a specified pressure. Equipment marking, labels, and IECX equipment protection levels, EPLs. What are the reasons for product certification? First, to demonstrate product quality with regard to the ability of the apparatus to function safely in a hazardous environment. Second, to enhance market acceptability by inspiring confidence in those involved in the selection, purchase, installation, operation, and maintenance of approved/certified products. Third, to improve quality and safety control. The ATEX Directive 94/9/EC, ATEX 95, was adopted by the EC to enable free trade of products between member states through alignment of technical and legal requirements. The directive applies not only to electrical equipment but also to mechanical equipment and protective systems used in the presence of potentially explosive atmospheres containing gases/vapors or combustible dusts. The ATEX Directive 99/92/EC, ATEX 137, commonly known as the Use Directive, is implemented in the UK via the Dangerous Substances and Explosives Atmosphere Regulations 2002, DSEARs. Prior to the introduction of the ATEX directives on July 1, 2003, apparatus for use in hazardous areas were marked as illustrated below. Apparatus complying with the ATEX directives, however, will still be marked in this way but will have additional markings to indicate that the apparatus conforms with the ATEX directives. Apparatus approved/certified as providing a method of protection for use in hazardous locations are required to display the following markings: the symbols X, and the type of protection used, D, E, N, and the gas group IIA, IIB, or IIC, and the tier rating T1, T2, etc. Example 1, marking is XDIIBT3. In this example, equipment marked thus, X, as far as Europe was concerned, could only be used in the UK because it had been constructed to the British standard BS 4683, which was not a harmonized European standard. Apparatus constructed to this standard, however, was used in other countries out with the European Community. Such equipment would also be marked with the EECS Certification Authority symbol. Equipment certified in accordance with the IECX scheme will be marked X. Example 2, marking is EXDIICT4. For apparatus marked EX as in this example, the additional letter E indicates that the apparatus has been constructed to a harmonized European standard. Such apparatus would be marked with the EECS Certification Authority symbol as well as the European Community mark. Sample labels are shown, and it should be noted that the construction standard to which the equipment has been manufactured to, i.e. BS 4683, Part 2, BS 5501, Parts 1 and 5 and N50014 and N50018 are also given on the labels. For BS 4683 equipment, the IEC equivalent standard, i.e. IEC 79-1 in example. IECX compliant equipment will have standardized certification numbers which will include the abbreviation of the notified body's name followed by the acronym IECX, certificate issuer, the year of certification, serial number, and either of the suffix X or U where applicable, as shown below. IECX BAS 06. 1234X. First part is, IECX marking. Second part is the certificate issuer. Third part is the year of certification. Fourth part is the serial number. You will notice now very important letter mentioned at the last of the certification number which in sometimes be X or U. The X symbol at the end of the number of certificate, must be put when the device has peculiar conditions for a safe use. Let's doing some examples. There may be particular rules if the device is used in specific environmental conditions, such as in case of subnormal temperature or conversely in case of very high temperatures, or the gaskets may require specific treatments if exposed in chemical environments particularly aggressive. The conditions defined as normal for all equipment by the standard are: temperature, from -20 degrees Celsius up to +60 degrees C. Pressure, from 80 kPa, 0,8 bar, up to 110 kPa, 1,1 bar. Air with normal content of oxygen, usually 21% V/V. Therefore, the application of electrical equipment in atmospherically conditions outside of those intervals may need special rules. These rules are prescribed by the laboratory which emits the certificate and must be indicated by the manufacturer on the operating and maintenance instructions that are with the device. Sometimes the regulation may be directly indicated on the device, for example, if it is not possible using solvents to clean a transparent surface plastic made. Other times, being the regulations much long and complex, must be indicated necessarily on the operating instructions. The X letter at the end of the number of certificate has the task to warn the technician, the conductor, the maintenance technician and the inspector about the necessity of applying specific cautions to avoid malfunctioning dangers of the equipment and the consequent lacking of explosion-proof protection. What many ignore, maybe because they have not read carefully the standard, is that even on the equipment it may be a warning mark as an alternative to the rule of X symbol, which reports the indications of use in peculiar conditions. The manufacturer should ensure that rules relevant to special conditions for a safe use are provided to the buyer along with any specific information. Letter U means X component denotes an equipment that must not be used alone, but only inside a device or a system along with must be certified. In the common practice, the most common X components are the empty XD junction boxes, which have passed the explosion-proof tests in a qualified laboratory, but they are not certified with the specific electrical contents. These junction boxes should be certificated again by who will commercialize or install them as equipment. In practice, these junction boxes are tested by the manufacturer to ensure the mechanical strength against a potential internal explosion. The end user, that is who will make the cables entries and install the electrical equipment, should provide, independently, a certification as explosion-proof device. The X components should be marked as the main equipment, reporting the U letter at the end of the number of certificate, in such a way it's evident that to be installed in areas with potentially explosive atmosphere, must get an additional marking which clearly indicates the compliance to ATEX directive and the number of certificate as manufacturer. Unfortunately, it happens that many end users do not get the necessary knowledges and they are sure to be able to drill the enclosure's sides and to install the most different electrical equipment inside. This goes against the safety principles of equipment and it is absolutely forbidden by the standards. The meaning, often ignored, of U and X characters inside the certificate, represents one of the problems that frequently cause disagreements through the chain from the manufacturer of junction boxes, to the inspector, passing across the technician. Those are not simple topics to understand and, for this reason, we invite you to study very well the relevant points of the standard which treat them. In conclusion, we remind that U and X symbols must not be present at the same time on the same plate, because the previous one indicates a component and the second one a device. Equipment Protection Levels, EPLs. Category Definitions. Group 2 Category 1, very high level of protection equipment. With this category of protection may be used where an explosive atmosphere is present continuously or for long periods, i.e. Zone 0 or Zone 20. Group 2 Category 2, high level of protection equipment. With this category of protection may be used where an explosive atmosphere is likely to occur in normal operation, i.e. Zone 1 or Zone 21. Group 2 Category 3, normal level of protection equipment. With this category of protection may be used where an explosive atmosphere is unlikely to occur or be short duration, i.e. Zone 2 or Zone 22. Group I Category M1, very high level of protection equipment can be operated in the presence of an explosive atmosphere. Group I Category M2, high level of protection equipment to be de-energized in the presence of an explosive atmosphere. The introduction of equipment protection levels, EPLs, enables a risk assessment approach to be implemented for the selection of explosion-protected equipment in hazardous areas. This provides an alternative to the traditional method of selecting equipment to suit the zone, which does not take into consideration the consequences of an explosion. The table below shows the zones where both ATEX categories and EPLs may be used from a traditional selection approach. Equipment protection levels, EPLs, are available for both gases and vapors and also combustible dusts as illustrated in the table below. Equipment marked G is for use in flammable gases, vapors or mists, and for use in combustible dusts when marked D. EPL definitions. Group 2 gases. GA, equipment for explosive gas atmospheres, having a very high level of protection, which is not a source of ignition in normal operation, expected faults, or when subject to rare faults. GB, equipment for explosive gas atmospheres, having a high level of protection, which is not a source of ignition in normal operation, or when subject to faults that may be expected, though not necessarily on a regular basis. GC, equipment for explosive gas atmospheres, having an enhanced level of protection, which is not a source of ignition in normal operation and which may have some additional protection to ensure that it remains inactive as an ignition source in the case of regular expected occurrences, for example, failure of a lamp. Group 3 dusts. DA, equipment for combustible dust atmospheres, having a very high level of protection, which is not a source of ignition in normal operation, or when subject to rare faults. DB, equipment for combustible dust atmospheres, having a high level of protection, which is not a source of ignition in normal operation, or when subject to faults that may be expected, though not necessarily on a regular basis. DC, equipment for combustible dust atmospheres, having an enhanced level of protection, which is not a source of ignition in normal operation and which may have some additional protection to ensure that it remains inactive as an ignition source in the case of regular expected occurrences. Thank you for your watching. Subscribe to be notified for the next parts of our program.